Hi everybody, Mr. Wickens here, and in today's episode we're going to talk about some everyday forces and how we show them with something called a free body diagram. So after today's episode, you're going to be able to draw a system diagram, a free body diagram, and apply them to different dynamics problems. What dynamics problems are just problems that have forces in them. We're going to describe and define some everyday forces, similar to the last episode where we talked about the fundamental forces. And then we're also going to take a look at what the difference between an external and an internal force are. So what we're going to do is we're going to start by looking at this situation. We have a little girl on the left-hand side and a little boy on the right-hand side. And to me, what they're trying to do is they're trying to move this wagon to the right. So they're trying to move it in this direction. Together. And so you can draw a system diagram and a free body diagram to simplify what you're trying to show here so that you don't need to draw something complicated. And so how physicists and scientists draw that is using something called a free body diagram. And here we have a free body diagram. It's this box here with a dot in the center, and dot in the center just helps you have somewhere where you can start drawing which way all these different forces are acting. So first we're going to start with the little girl. She's pushing the cart to the right. So we're going to draw an arrow that starts from the center and moves to the right, and it's going to be the applied force. She's applying a force. We could have also labeled it something like F1, force 1, but just saying that there's a force being applied in the right direction. The reason that we used this FA is because I wanted to talk about what happens with little boy on the right using a rope to pull the cart. Whenever you have a rope involved, you're going to have something called tension involved. So to show tension, we use FT. So we also have a force to the right with tension, and that's from the rope. Next, we have this thing called the normal force, and we're going to talk a lot more about the normal force in coming episodes, but what it is it is a force that's perpendicular to the surface that the object is on. So if you want to think about it like having a textbook on your desk, the normal force is going to point straight up. If you had a textbook on an angle, or you have an object on an angle of a hill, the normal force is going to be to a right angle of that object. And that perpendicularness is going to become more important in later episodes. So the next force, and we don't always include this force in our problems, but it's friction. And what friction is it's just a force that resists the motion or any attempted motion of an object. We're going to talk a lot more about friction in episodes to come. But the important thing to know is it acts in the opposite direction of applied force. So far we've talked about a bunch of forces that are contacting the wagon. We have the normal force, which is a contact force because it's the wheels touching the ground. We have the tension force because that's a rope touching the wagon. We have an applied force because that's the girl who was pushing the cart. We have the friction force because that is the force from the ground to the wheels of the wagon that's resisting the motion of the wagon. So those are all contact forces because they're touching, they're making contact. There's also forces that are sometimes acting at a distance, and we call them non-contact forces. Probably the most common one that we deal with on a day-to-day basis is gravity. So the force of gravity always pulls towards the Earth's center. And in this case, it's opposite to the normal force. If we want to talk a little bit more about gravity, there's a pretty simple equation for gravity. The force of gravity is the mass of an object in kilograms times gravity's acceleration in meters per second squared. On Earth, the gravitational acceleration is 9.81 meters per second squared, which you probably learned in Science 10. So just to summarize, the everyday forces that we talked about is the normal force. It's the force that acts perpendicular to the surface where the object is resting. we have the force of gravity, which is the force that attracts two objects together. In this case, the object being attracted to Earth. If we weren't on Earth, the gravitational acceleration would change, but we'd still have a force of gravity unless we were in the middle of space or something like that. We have the friction, then we have the friction force, which opposes the attempted motion of the object. It wants the object to stay in the same place. It resists the motion. We have the applied force, so it's a contact force, a pushing force or a pulling force. And then we have the tension force, and it's also applied force, but it's a specific applied force when you have a rope or a string. Okay, so now that we've talked about some different types of forces, we're going to talk about the difference between an external force and an internal force. In this unit, we're mostly going to focus on external forces. So what an external force is when an object pushes or pulls on another object. So we have this diagram here. We have two figure skaters. An example of an external force would be the force of if the skater 1 pushed on skater 2. So we could draw that applied force in the right direction from skater 1 to skater 2. An internal force is when an object exerts a force on itself. And those are just important to have an idea what they are. So in this case, an internal force would be a force when skater 1 pushes on skater 2. There's an internal force that skater 1 exerts on itself because skater 1 is going to go backwards, and we'll talk more about that in Newton's laws. Alrighty, so now some free body diagrams. If we look at some of the illustrations below, we have a fish on a line in A, we have a volleyball being held up in B, and we have a Physics 11 book, in fact, on a desk being pushed across the desk. So let's look at situation A first. So for the fish on a string, we have the force of tension and the force of gravity acting on that fish, and that is all. You could also draw the fish as just a box if you want it a little bit simpler. For the volleyball, we have the normal force, the force perpendicular to the hand holding the ball up, and the force of gravity pulling the ball down. And then in a more complicated system, we have our physics textbook. We have the force of gravity pulling the textbook down. We have the normal force, the force perpendicular to the desk, pushing the textbook up so it doesn't fall through the desk. We have the applied force of the hand pushing it to the right, and then we have the friction force resisting that motion to the left. What you'll notice for all these diagrams, it's important to say what your positive direction is. We usually say that up is positive and down is negative, right is positive and left is negative, but you are welcome to change that. Sometimes when we look at things falling, it's easier to think that down is positive, just so we don't get confused with a bunch of negative numbers. So we looked at some examples of free body diagrams, but this is kind of what the definition of a free body diagram is. So free body diagram is a simple drawing that represents whatever object or thing you're looking at, and it shows all the external forces on it. It doesn't include internal forces. It doesn't include any forces that the object is exerting on itself. So some steps to draw a free body diagram. So what you do is you draw a box or a point that's going to represent the system under analysis. I usually like to use a box, but you can also just draw a point. Then you're going to draw direction arrows of all the different forces acting on the box. And you're going to start the arrow from the center of your box, or the point, and you're going to go out from the box. Usually the size of the arrow kind of represents how much force is acting on that object, and that's going to help you decide if the object is moving or not, and it's good for illustration. It doesn't need to be exact to scale, but it should be roughly the magnitude. And the last thing you're going to do is you're going to label all the forces so that you know what the force of gravity is. The force of gravity is not acting in the up direction, and it's clear to you and to anyone else looking at your diagram what all the forces are. So there's just 4 basic steps. So with these free body diagrams, it's going to show us if the object is accelerating and changing in velocity based on if there is a force or not. So we're going to look at a couple examples here. So if we were to draw a free body diagram of a book at rest on a tabletop, because I've mentioned that a few times in this episode. So we have our box, we have gravity acting on the book, and we have the normal force acting on the book perpendicular to the surface of the table. The book's not moving, and that's it. Pretty straightforward, I think. The acceleration of the book, because the book's not moving, it's at rest, is 0. Okay, next one. A girl is holding a rope suspended from the ceiling. So here we have a free body diagram. We have gravity acting on the girl, and then we also have force of tension because we're dealing with a rope pulling the girl up towards the ceiling. Finally, there's no acceleration because the girl is not changing velocity up or down. An egg is free falling from a nest in a tree. Neglect air resistance. Neglecting air resistance is something we're going to be doing quite a lot in this unit, and it makes the calculations a lot easier. So here we're going to draw a free body diagram, so a box representing our egg, and the force of gravity is pulling it down. There's nothing acting on it in the upward direction, so the acceleration is going to be 9.8 meters per second squared down. So if we wanted to look at the egg falling again, but with air resistance, we could just draw the same diagram, but instead we'd have our force of gravity down, force of air up. The force of gravity is obviously going to be bigger than the force of the air resistance. So again, our acceleration is going to be in the downward direction, but it's going to be probably a little bit less than in the previous problem. Okay, next. A right forward force is applied to a book to make it move across the desk. Consider friction, but neglect air resistance. So again, we're going to draw our box. We have a big force to the right, a smaller force to the left because friction is resisting us trying to push the book across the desk to the right. Then we have our gravity force and our normal force perpendicular to the desk there. So a car is stopped at a light. This is going to look pretty familiar to our first problem. Again, instead of representing a book with just a box here, we're representing the whole car with a free body diagram. We have gravity acting on the car and the normal force acting up. The car is not moving, so the acceleration is 0. So here we have a car coasting to the right and slowing down. So this is probably the most complicated of all the different problems we've looked at so far. So there's no force being applied in the right hand direction. It's just coasting. So we have gravity again and the normal force, but since there's no force being applied to the right, we don't draw an arrow. We know it's moving at some speed, but it's slowing down, so the acceleration is going to be the negative, and what's causing that acceleration to be negative is the force of friction, which is acting to the left. Okay, so the force of friction causes it to slow down, and that's because no one's pressing on the gas. The car is just slowing down. For any of you with driver's license, you might notice when if the light ahead of you is red, to save your brakes, you might take your foot off the gas. You're not applying force anymore, and your car will slow down a bit before you get to the red light and have to apply the brakes, and that's because of friction. So yeah, our acceleration is to the left. All right, thanks everybody for listening. If this was a good video, please like it. And if you have any feedback that's constructive for future videos, please let me know in the comments. I am trying to improve. This is new for everybody. I hope this was helpful. Have a great day.